Hey, so today we are gonna look at Dirty Frag. So this is a vulnerability that in which the kernel allowed network packet fragments to reference protected file page cache pages. So before going into it, let's just first understand all these things step by step, and then we will go through it the whole vulnerability. So first of all, let's understand whenever we access any file, for example, an etc password, if we are accessing it in Linux. So what happens is whenever we access it, the Linux store it in a cache memory. So that cache memory is basically the page cache memory, what we call it in Linux. So this gets stored in page cache. So the page cache contains multiple pages here. So what I mean by multiple pages that each page contains the information about the etc password. So each page has a size and each page has a reference. So whenever we are accessing the etc password, it gets cached in the page cache in the multiple pages. So whenever in the second or third time and any time when we are going to access it, the Linux is going to prioritize the page cache over the disk memory because it is faster, it is stored in the RAM. So this is a key point here that Linux prioritizes cache memory over the disk memory here. Now let's take a simple example here that suppose we take a file and we have to use it somewhere or send it somewhere else. Suppose we are uh, doing a cat or file name and we are grabbing hello from it. So the like this, if you can see, and here the cat is we are sending the command instruction and we're grabbing the hello message. So this is like sending and receiving part. So whenever the sending and receiving process follows, the information is going from one place to another. So that process takes through the pipe. Linux need a temporary place to hold that data while transferring it, and that is called file. So it is like a temporary channel, and inside that pipe, Linux always keep a RAM memory also that is called pipe buffer. So we have two things here. First is pipe, and second is pipe buffer. So pipe buffer, as I've told, this is just a temporary RAM memory that is used inside the pipe to allocate that space. What happens inside that pipe buffer, we will see. So whenever we are transferring when one program to another, for example, program A to program E, it will go through the buffer. So what happens inside the buffer, whenever it is doing any work, what it does is it always creates a copy of the file or whatever it is receiving. Suppose we have given it to do a cat of etc password. So what will it do? It will copy the whole command into the buffer and then point it to the grab. So before giving it the grab to grab the hello message, what it will do, it will create a copy of it. So what happens is the etc password data goes through the pipe buffer here and then goes to the grab message. So in the process, what happens in a normally that it creates a copy of it each time. So it reads the file, it creates pipe buffer and copy file data into the pipe buffer. So after this, we have always two copies. First is the original file page and second is the pipe buffer copy. So let make it more example oriented. Let's say we had this etc password data. Okay. So when we access etc password access, it gets stored in the page cache. So it gets stored in the page cache, and suppose we are naming it here page, the in which page the information got stored. Let's suppose the page reference name is this 0xabc. We are naming it just that. And what's gonna happen here now, it had created two copies. First is the original file page, that would be this, and second is the copy buffer file. When it accessed the etc password file, it created a copy of it in the RAM only. So it has now two copies. First is this and second is this. So this is so to solve this copy, to remove the duplicacy, what Linux introduced is called a Linux optimization called Splice. So this is the key thing here. So what it does is uh, it basically says that I have already stored the page cache of this at this reference, then why to create another copy. So what it will do when we'll run a splice command and give it a reference, so it will not create a copy, and what it will do, it will use this original file page as a reference here. It will use this as a reference here, and instead of copying the data, so instead of copying this data, the original file phase will go to the grep here. If I make it larger, let's see. So after Splice running, what happen is that it reads the file data, create file, but it does not create the copy. What it does is it uses that already existing page cache that is already there. Before Splice, we have two copies. One was original copy, one was pipe copy. But after Slice, we will only have one copy, that is this, and it will be used at every place whenever we required the etc password file. So this was about Splice, and it is also called the zero copy optimization also. So after Splice, the next thing comes is SKB. So SKB is basically the kernel structure to network packets. So it is basically a short form for this structure SKBIF, and it contains multiple data like TCP, UDP header, packet data, metadata, and fragments. From this, we will focus currently on fragments. So fragment contains certain data like the page, offset, and length. So if you see here, the important term is there is the page. If you see here, the page cache contain multiple pages here, and the fragment also contain the page reference. Suppose we have loaded the etc password already in the page cache, right? And we have run the splice command. So what will happen whenever we have to access the etc password? It will not create the copy. It will directly use this page cache. Got it? So whenever an fragment gonna come with this page reference, it's gonna it's gonna point it to this. It's gonna point it to this. The page will reference here. Now comes second thing, the ESP and RPC. So these system process packet fragments and they can perform modification also. So what happened is the ECP and RPC, ESP and RPC get used to for the modification, and it is basically for the process of fragment. If it contains this, what happens is that kernel think that it is modifying the packet data, but instead it is not, because the page is currently mapped to this, and this is basically the SKB point to page cache, that is protected etc password cache memory. So it is thinking that it is modifying the packet data, but instead it is modifying the protected etc password cache memory. And we have in the start we have told that Linux always prioritize the cache memory over the read disk file memory. Suppose we have a file that contain this. So this is this file, etc password file, and it has a password which gives reference to X. After the modification, what is going to happen? This file is going to change to this. Now the X is gone here. So now for the root user, the password is not required anymore. That means password is gone here. So now page cache got updated. So what happened here? The root file, the disk file is as it is, but the page cache got updated because it referenced here, and we gave the instruction and the data and payload to modify this data and remove the X. Now the password is gone. So the current user, whenever it switches to the root user, what it will do? It will first try to get the information about the user from the page cache. And here it got updated that it does not require any information password. So it will allow the user to act as a root user. So for any, so Dirty Frag is just happened because the Linux kernel allowed network packet fragment to reference protected file paged cache pages. So this was about the Dirty Frag, and it is kind of similar to the pipe vulnerability. Also, you can look of it in that the main uh, the main thing was in 35 was pipe buffer, but in this currently the main thing is fragment. In the fragment way, it is using the page here. So that was for today about the dirty frag.